Hey there, this is Mathcamp321, and in this video I'm going to show you how to take the graph of a function and sketch its derivative. In example 1, we're shown the graph of a horizontal line f, and our job is to sketch the graph of the derivative, or f prime. There are several ways you could go about doing this, but what I'm going to do is identify 3 arbitrary points on this horizontal blue line. I've identified 3 points on the horizontal blue line, naming them A, B, and C. Now what I'm going to do is draw in the line tangent to the blue horizontal line at each of these 3 points. At each of the 3 points, A, B, and C, the tangent line itself appears to be horizontal, just like the blue line. What would be the slopes of these orange lines at the 3 points A, B, and C? To me, since they're horizontal, they look like they're going to be 0. No matter where I am on this blue line, the tangent line will have a slope of 0. So my conclusion will be that the derivative graph will be the line y prime is equal to 0. And I'm going to go ahead and draw that in green. Let's take a look at the next slide. In example 2, I'm shown the graph of f. Again, it is blue, but this time it is a sloped line. And what I'm going to do is the same method that I did in problem 1. I'm going to pick 3 arbitrary points on this blue line and name them A, B, and C. Using an orange pen, I'm going to draw the line that is tangent to the graph of this blue line at each of the 3 points. Since there's no scaling provided on the axes, I can't say for sure what the slope is, but I do know that it's something positive because the line is increasing. So I'm just going to guess and approximate the value to be about 1. At each of the 3 points, the slope seems to be about 1. So now I'm going to go ahead and draw the derivative graph in. And again, no matter where I am in the blue curve, the derivative appears to be about 1. Okay, let's move on to the next slide. In example 3, we're given what looks like the graph of an absolute value function because of this thing that looks like the letter V. And my objective is to draw the derivative of this graph. So like the first 2 examples, I'm going to pick a few arbitrary points that lie on this graph that looks like a V. I'm going to name those points A, B, C, D, and E. Now that I've identified 5 points on this graph, I'm going to draw in the line that is tangent to the graph at each of these 5 points using an orange pen. You'll notice I never drew in a line at point C, and we'll discuss the reason why in just a moment. But if I look at point A and point B and I think about what the slope of the tangent line would be at each of those points, the first thing that I realize is that because the line is decreasing, I know that the slopes are going to be negative. Again, there are no scales, so I'm just going to approximate what I think the slope is going to be. At point A, it looks like the slope is -1, let's just say, and that would mean the slope at point B is also -1 because the steepness hasn't changed. So I'm going to go ahead and write that in. Moving to the right arm of the V, we have points D and E. Again, there's no scaling, so I'm just going to approximate what I feel like the slope might be. Because this arm is increasing, I know that the answer is going to be positive for the slope. I'm going to approximate the slope of the line tangent to the graph at point D to be +1, which means that the same thing would happen at point E. So I'm going to go ahead and write that in. Now in this course, we learned 3 reasons for non-differentiability at a point. And one of those 3 reasons was if there is a cusp or a sharp turn on your graph, it will be impossible to take the derivative there. So at point C, we see that there is a sharp turn or cusp. As a result, I'm not going to be able to take the derivative at point C. So what might happen is we might have some sort of asymptote there, or we might have a hole, or the graph might just abruptly end. Let's take a look at the derivative and see what makes the most sense for this case. So I'm going to switch to the green pen now because I'm ready to draw the derivative. So for the first arm, we've noticed at point A and point B, the slope was -1. In fact, any point I pick on that leftmost arm of the V will be a slope of -1. So I'm going to go ahead and draw that in. Now you'll notice I put an open circle right above the point C. The point C is non-differentiable, so I'm not going to be able to take the derivative there, so there's not going to be an actual green graph. That's why I made it the open circle. Moving to the right arm, any point you pick on it will have a slope that is +1. So I'm going to draw a line at y equals +1. And again, I'm putting an open circle at the end of that because point C is non-differentiable. So we end up getting as our derivative graph this piecewise graph that has a step down at -1 and another step up at +1. Let's move on to the next slide. In the fourth example, we're given a piecewise function with 3 pieces. And hopefully at this time you're getting a sense of a little bit of a process that might help you to sketch the derivative given a graph. So like the first 3 examples, I'm just going to pick a series of arbitrary points on each of the 3 pieces. Now that I've identified those points, I'm going to draw in the lines that are tangent to the graph at each of these points. Now there's no scaling including on these axes, so I'm just going to approximate numerically what these slopes are. At points A and B, the numbers are going to be negative because the line is decreasing. I'm going to say the slope is about -2. As I move to the middle section, the slopes at point C and D are going to be 0. As I move to the piece that includes points E and F, the slopes appear to be positive, but less so than the segment containing points A and B. So if those had a slope of -2, I'm going to call the slopes at points E and F +1. And now with my green pen, I'll draw the 3 resulting pieces for the derivative. The first piece is going to be consistent line at -2. The middle piece have slope of 0. The rightmost piece is a slope of +1. You'll notice again that the original blue graph has 2 sharp turns or 2 cusps. And at those 2 locations there is actually no derivative and hence we have the open circles. Let's move on to the next example. In example 5, we're given the graph of a parabola and we're supposed to draw its derivative. So a couple of new things are going to happen in this problem, but I'm going to start off the same way, and that is to identify a few random points on this blue curve. Now that I've identified these 5 points, I'm going to go ahead and approximate the tangent line, or the line tangent to the graph at each of these 5 points. The next observation that I'd like to make is a new one, and that is we're starting with the graph of a parabola, which is a quadratic. In the most simplistic state, this can be thought of as y equals x squared. If we were to actually take the derivative of y equals x squared, we'd end up getting y prime is equal to 2x. It's going to be the case for every quadratic that its derivative will be linear. So what I'm about to draw is going to be a line. I've been drawing all my derivatives in green, so I'm going to be consistent and do the same thing. But before I do that, I need to approximate the slopes of the tangent lines at each of these 5 points. At point A, we've got something negative and kind of steep. I'm going to say that the slope is about -3. At point B, it's still negative, but it's a little bit less steep. I'll say the slope is equal to -2. At point C, the tangent line is horizontal, so I'll say a slope of 0. Okay, at point D, we've got a tangent line that is now positive, so I'm going to say that the slope is maybe +1. And at point E, it's still positive, but it's steeper, so I'll say +3. Okay, so let me grab my green pen. At point C, the derivative is 0, so I'm going to put a point right here on the x-axis. All the points on the left arm of the parabola have slopes that are negative. So if the derivative is negative, that means it's going to exist below the x-axis. After point C, all the slopes are going to be positive, which means it's going to exist above the x-axis. Now keep in mind that what we're supposed to graph is supposed to be linear. So it's going to be a line starting below the x-axis, and then it's going to be above the x-axis. So the green represents the graph of our derivative. And this concludes part 1 of the series of sketching derivatives given an original function. Stay tuned for part 2 where we explore more complicated graphs and their derivatives.